All right, all right, all right. Welcome back. We are heading onward to section 6.3, the standard normal distribution. Shun, shun, shun. You should have your handy dandy pre-printed notes here. And just to help you out, because I'm going to kind of go off the grid, off the script today a little bit. I put little pencils on the screens. See this little pencil? It means there's something on that screen for you to write down. If you don't see the little pencil, just listen, because I want you to have a better idea of what the standard normal distribution is. So the notes start off with what is the standard normal distribution. And yesterday we looked at the normal curve and how you have your IQ scores and how they're distributed, and it makes a nice little bell curve. The standard normal distribution is a normal probability distribution where the mean is 0 and the standard deviation is 1. By the way, this is lowercase sigma. I know I've been calling it little fishy. I finally looked it up, but this is sigma. It's just the lower one. The big one looks like a big E, the capital sigma. But moving onward. So here's what it'll look like. You've got your z-score down here, and you've got your 0 in the middle, and you've got your bell curve. The total area under the curve is 1. So I'm going to take a step back and look at the IQ distribution. So when we had this before, the IQ score was set up. This is the normal distribution. We had the mean was 100 and the standard deviation was 15. Well, if we were putting this on our bell curve, since it's a normal distribution, the mean would go here in the middle. That's 100. And then since one standard deviation is 15, I would add 15 to this to get 115. So this is the mean plus one standard deviation. And then I'd do the same thing on the other side, except I'd subtract 15. So 100 minus 15 is 85. And so on. So to go out 2 standard deviations, I would add 2 times 15, which is 30, to 100. So that gives me 130. I'd subtract 30 from 100 to go to the other side to give me 70. And so on. So I'd add 3 standard deviations to 100, which is 3 times 15. So it'd be 145, and I'd subtract that over here, 55. So these are your IQ scores. And just because you might be curious of what is an IQ, call it intelligence quotient, and they give you a little test to determine what your IQ is. And it can change. The thing they have found that causes lower IQ more than anything else is isolation. If you're only around a certain type of person or you're totally isolated, that tends to diminish your IQ. So if we look here, average is in between one standard deviation. So they say this is your average intelligence. You'd have an IQ between 85 and 100. Above average would be between 100 and 115. I think I'm in that range. A little bit above average, but I'm just average like most people. And you see 68% of the population would fall into that range. 68% of the population would have an IQ between 85 and 115. Then as you move outward 2 standard deviations, this means 14% of the population would have IQ between 115 and 130. So this is a high intelligence on this side, and its counterpart is low intelligence over here. So if you score below an 85 on an IQ test, that's not necessarily good, but you can still have a nice life. And so between those two, 95% of our population falls between 70 and 130 on the IQ test. That's what this means, this normal curve. You can do things with the percentages like figure out how many people that is and so on. And if I go out even further, this would be mentally inadequate. So mentally impaired people would be in this category. And over here is superior intelligence. Then to the far right, or far left, box of rocks. I don't know how else to put that. Box of rocks is what I would call that mental IQ. And over here is exceptionally gifted. 0.01%. That's 0.001 is not very many. That's 1 out of 1,000. And if you're curious, Einstein's IQ was 160 plus. That's actually 1, 2, 3, 4 standard deviations above the mean, which is very improbable. If we're trying to put this on the standard scale, I want you to understand the correlation. This is just a normal distribution. It has its mean in the middle, and then each of these little subdivisions are a standard deviation apart. But if we wanted to put this on the z-score, the z-scores, you'd have your mean is a 0, and this means 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean, and so on. And this would be going to the left of the mean. They do that z-score as a negative. Negative 1 means you're 1 standard deviation below the mean, 2 standard deviations below the mean, and 3 standard deviations below the mean. I want you to be able to understand that. It's not difficult, but people get confused when they put the zeros and ones. That just stands for standard deviations. Math people don't like to write a lot, so they standardize it, make a table, make their life easier. We don't like a lot of wordiness. Even we simplified this so we didn't have a lot of numbers down there. Now, the reason we really care about z-scores and area under the curve is that there is a correspondence between area and probability, and I want you to make this distinction here. So here's our IQ distribution, and when we put the z-scores on there, this would be 0, 1, 2, and so on. But 34.13% is this little block here. That's in decimal form 0.3413. This is what you're going to find on the table, and this is the area, square units. I should put square units, I know, but this is the area under the curve. And here's where our z-scores would be. And what you're going to be doing is you're going to be either finding a z-score or being given a z-score and finding the area under the curve, but that's the same as the probability. If you get that in your brain, it makes it much, much easier. So probability of having an IQ between 100 and 115 is 34.13%. That's this percentage here. That's the probability, and you have all your nice words and everything there. That's a probability. The area under the curve between 0 and 1 standard deviations, or when z is between 0 and 1, is 0.3413. It's the same thing. You wouldn't put a percent for that. But this is the thing you're going to find in a table, except you're not going to get nice whole numbers like that. You're going to get like 1.78, and you're going to have to look it up on a table. But if you can kind of get that concept that area and probability, it's the same thing, they're just written differently, and this area is the probability, this will make this a snap. So to convert normally distributed variables to the standard normal distribution, you can use this formula. Your data value minus the mean over your standard deviation, or z equals x minus the mean over the standard deviation. So this is mu and this is sigma. Once x values are transformed using the preceding formula, they are called z-values. I'm not speaking German here, z-values. The z-value is actually the number of standard deviations. Keep that in mind. Z-value, standard deviation, it's the same thing. That a particular x is away from the mean. Positive means it's to the right of the mean. Negative means it's to the left of the mean. Easy. You guys can get this stuff. Now, just to show you an example of doing the data values, if I were to take 115 minus 100, that'd be 15. Divided by the standard deviation of 15 would be 1, 15 over 15. So that's what they're getting at there. So here is your formulas again. If you need to pause it, this is on your notes. Finding probabilities given z-scores. This is the main idea. This is what you want to be able to do with these. You've got a table E, an appendix of your book. It's on page 770. You may want to pause it and open your book there, because I'm going to be showing you how to use this table in just a second. You also have the table here. There's like an important formula card that came with your book that it's right here, and you might want to keep that handy. So if you have that one, it's the same table. You can also use, the formulas table, I just showed you that, and you can find the areas for different regions and add or subtract. That's the idea of how to find the probabilities using the z-scores. Graphing calculators, I'll also show you how to do it with the graphing calculator. So here's what the table E looks like, and like I said, it's on page 770. This area in here, these are the areas under the curve between the mean and that z-score. So right here at the bottom, you'll notice it only goes out 3, and it's got 0.4999 at the very bottom. Well, why would it only go out 3? Because you've got positive 1, positive 2, positive 3, and you got the negative ones. Well, the reason is, since this is symmetric, which remember symmetry, it folds right on top of itself, the z here would be equal to the opposite of z on this side. So if you got like a negative 1.2, you're going to look up a positive 1.2. It'll be the same area. Also, it only goes to 3 because there's not significant data out to the other side. That's almost half of the whole thing. So you're going to get close to 99.99999%. So that's why they stop at 3. Now, looking at this, I was just showing you here, this is the whole shebang. The mean plus 3 standard deviations, and that would mean a z-score of 3 here, is out this way. If you add these up, you're getting very close to 1. And beyond that, that's like, what, 0.001, I said, for Einstein? That's why they stop it there. All right, so let's look at what this means. All this body, all these numbers here, is the area under the curve between 0 and z. That's this area right here. If you're good at geometry, you'll know when to add and subtract and so on. Also, if you keep in mind, from 0 all the way to the right is 0.5. So you know half of it is 0.5 and the other half is 0.5. You'll add and subtract from 0.5 and so on. The z-scores, this is the first 2 digits, the whole number and the tenths place for the z-score is going down this way. And then to get the hundredths digit of the z-score, that's along the top. All right, so let's say I had 0.71 for a z-score, and I wanted to know the probability for 0.71. Well, here's 0.7, and then I'd go over to the hundredth spot to get this probability right there. Area under the curve, probability, la misma cosa, the same thing. All right, so let's look at this. 4 steps. So this is on your notes. Here's what your basic gist is to find the solution of problems using the standard normal distribution. First off, you're going to draw a picture and you're going to shade the area desired. That's going to tell you whether you can just use the z-score straight, whether you have to add it to another z-score, whether you have to add the areas together, whether you have to subtract the areas from 0.5 or add 0.5 to the areas. Then you can find the correct figure in the procedure table, page 290 to 292. You can look this up. Most of you will be able to just do this logically. Alrighty, or you can use a graphing calculator. The graphing calculator will give you the area under the curve between 2 z-scores, easy peasy. Follow the directions to get the desired area. I'm going to go ahead with the procedure table in your notes, but know that you could stop the video here and fill it out from page 291 to 292. I'm going to do the examples for this in a different video because I think it's getting too long. Here's the 7 basic types of problems that you're going to encounter when you're looking for areas / probabilities given the z-scores. So if you have just 0 and any z value, that's the easiest one. You shade it. It could be to the left. It could be to the right of the mean. You just look it up in the table. That's all you have to do. Now on your notes, they have the instructions on the left-hand side. All you have to do is do the sketch of the picture. Then you can refer to your notes to figure out what you're supposed to do. In any tail, want to find some tail? Look up the z-value to get the area. So this is what the tail looks like. It goes to the right. Keep in mind, half of it would be 0.5. So you're still going to look up the area on that table, but you're going to subtract it from 0.5. So that's pretty self-explanatory. Between any 2 z values, you're going to find the bigger area and subtract it. So that's what this one looks like. You got 2 z's on one side of the mean. This is saying it's on the same side of the mean. You find the bigger one, find the smaller one, and subtract it, because the bigger one's going to be the area from 0 all the way over, and the smaller one's going to be from 0 to here. So if you subtract those 2 areas, bada boom, you got it. But if they're on opposite sides of the mean, that's easy. You're just going to add them together. So you get the 2 area values for those z-scores and add them up. To the left of any z value, where z is greater than the mean. So in other words, they want this area from here all the way down. Well, this is where you have to know this whole side on the left is 0.5. So you're going to take 0.5 plus the area you find in the table here. So that'll give you that whole thing. to the right of any z value where z is less than the mean. So you're going from here all the way to the right. Remember, this from 0 all the way over is 0.5. So you get the area out of your table between 0 and z and add them up. In any two tails, you're going to have to do a combo of the two tail things. So you're going to take 0.5 minus your z-score on this side, 0.5 minus your z-score on this side, or I'm saying z-score, but what I mean is what you look up on the table, and then add them together. We're going to stop right here and do the examples on a second video so that they're kind of split up a little bit. I hope this helps you understand z-scores, areas, and probabilities a little bit, and then we'll get into the minutia. See you later.